Bam. Now we're recording. Okay. So starting off here. So the last thing to cover is what's called the common ion effect. And this essentially is Le Chatelier dealing with this kind of scenario. We are talking about Le Chatelier. So that being said, what do we remember about Le Chatelier?
He was French.
Okay. And?
He was a chemist.
Uh-huh. What the hell was his principle?
Oh!
Remember we used to call him the LeBron instead of the LaShawn? No. I mean, that's what I used to call. Okay, that's actually. I'm going to just go back over.
I feel like...
this was the thing where you had to shift the arrow about which side had more things. And
Yes.
So the gas guy?
No.
Oh, this is not the gas.
So like,
He was,
if you one of the products, you have to increase something else on the product side to
Oh, so like if it's an exothermic reaction and I add heat, then it's gonna shift towards the left.
Yes, this is all the stuff, as Felicia says, he's the pokey one talking about shifting the reaction right or shifting the reaction to the left. So this is a special case of Le Chatelier's talking about shifting when we're talking about solubility equilibrium. So the thing to remember here is shifting to the left means we're going to make solid, right? And a shift to the right means you are going to dissolve, right? More soluble. So there's not a whole lot of things here that can be involved in the shift because remember, the solid itself is not part of my equilibrium expression. So changing the amount of solid does not actually affect your equilibrium. The only thing that you can actually do that will affect equilibrium is change the ions, okay? So that's the only thing that we're really primarily focused on. So we're dealing with the presence of ions, and of course, temperature can still shift. They don't normally mention temperature in terms of solubility equilibrium, so we're going to focus here on this part, this presence of other ions, and that's why it's called the common ion effect. Because at this point, when we've been talking about solubility, we've been talking about solubility in water. But what if for whatever weird reason, you weren't trying to dissolve the solid in water? What if you were trying to dissolve the water in a solution of something else already? That's what this is all talking about. So we are going to so that's what we're going to talk about, is if we're actually dissolving the stuff in something else. So for instance, if you were trying to dissolve silver carbonate in a solution that already had carbonate. So if I'm trying to dissolve it in a solution that already had carbonate, you can imagine if we were talking about our shifting principles, if you already had carbonate, it would be like having more of this way, in which case, what does the reaction do? Which way does it shift?
Left.
Left.
And you would end up with more of the solid. That's all common ion is. It's saying, I already have some of this stuff, therefore I will dissolve less of my solid. So in general, the general principle here states that the solubility of a solute, right, which is a solid, is decreases by a second common ion. So it's very similar excuse me, it's very similar to what we were just doing. And the calculations are also very, very similar. It's basically the only way to spot this is you spot this problem because you aren't talking about just water. Right? You're trying to dissolve your solid in another solution. And that's how you're going to recognize you have a quote unquote common ion problem. So with that being said, I wasn't going to do the quick check on the next page, but I was going to take that space, that big chunk of space on page 256 to write some stuff down.
Ms. Baskin?
Yes, sir.
I had a question. So when it shifts, you had said that it will the solid will dissolve less.
Mm-hmm.
So it's not that if there was already some of this thing in the solution you're dissolving, like if there was already carbonate in there, it's not that it'll end up making more solid, it's just less of it will dissolve.
Correct.
Okay.
It basically prevents it from dissolving because it's like, oh, I can only dissolve so much because there's already some of that stuff there.
Okay. Thank you.
Uh-huh.
Okay.
Yeah.
Will any of that ever cause it to like shift right instead?
No.
Of that?
No. The one thing you could possibly do is remove some ion through another process that would draw the reaction to shift right to make it dissolve more. That's not typically how they ever frame common ion problems, and it's not how we often look at it. So we will just exclusively be focusing on shifting backwards to decrease the amount. So let me go ahead and turn the page and take up this space here. So here's the thing. To solve these, we need to use an ice table. But we get to make a very good assumption. So if we were looking at that previous problem, right? The silver carbonate solid making 2Ag plus this guy. So for instance, if we assume that we were doing this trying to dissolve in a, say, 0.10 molar sodium carbonate solution, right? So what would that look like? Well, what it would look like is, since this is a solid, right? My ice table looks like this.
Wait, pause. What does that say? Dissolve in O?
Na2CO3, or that's 0.10 molar.
Oh, okay. Sorry.
Yeah, and this is the kind of universal abbreviation for solution, SL or SOLN. So if we have our ice table, do we ever put anything about solids in the ice table?
No.
No, we don't, right? So we can draw a line through that.
Wait, why not?
Because solids are not involved in our equilibrium expression.
Right.
So they're not involved in the actual calculation.
Okay.
So what are my initial amounts? Do I have any initial amounts?
No.
Sure I do.
The 0.1?
Yeah.
But it's okay, because it's 0.1 with the CO3, but is it going to be 0.2 with the silver?
No. It is only going to be 0.10 with this, silver is
Right.
not mentioned.
The
Okay.
things that aren't mentioned, we always assume are 0.
Correct. So we're saying it's like before you dump any of this stuff in, what is initially in the beaker of solution?
Yeah, we had
0.10 molar carbonate, but there is no silver in the solution.
Okay.
So you can imagine that at this point,
You're right.
now I'm adding this stuff, right? And so now as I add this stuff, what's going to happen? So if I'm using X at this point, because of this 2, this should be adding a 2X, right? Does that seem familiar?
Yes.
Okay. And since there is not a 2 here, what would this add right here on the carbonate?
Just X.
Plus X. So my equilibrium line would then be 2X and 0.10 plus X. So that being said, if you look, right, the KSP expression here would be an Ag plus squared and a CO3 2 minus, right? Which mathematically would give me a 2x value squared times a 0.10 plus x. Can you see that the algebra here would start getting tricky?
Yes.
Because of
Yes. Yes.
this, right?
Yes.
So we get to make an assumption. Here's the nice thing. It's like we assume that 0.10 plus x just equals 0.10 because the value of x is so small. That's our simplification, right? We essentially get to do that. Now the algebra is not hard because I don't have to deal with that polynomial in there. It's assumption you get to make in this kind of problem because our equilibrium values, those KSP values, are really, really small. And so therefore it doesn't, we get to ignore it. It's one of those instances where we do get to ignore it and life gets much, much easier. So I forgot to look up the KSP for silver carbonate. Give me some more room. Hold on. Silver. There we go. Okay. So the KSP value here is 8.5 times 10 to the negative 12. All right. And that's going to equal this 2x squared becomes what?
4x squared.
4x squared times a 0.10, which means it becomes 0.4x squared. So solving through the algebra, what would be the next step?
Divide by 0.4.
Divide both sides by 0.4. So 8.5 times 10 to the negative 12 divided by 0.4. It's going to give me 2.125 times 10 to the negative 11 equals x squared. And how do I get x?
Square root.
Square root. So 4.6 times 10 to the negative 6, right? So that's the solubility in the solution. Now you see the value of x and how small it is times 10 to the negative 6. If I had subtracted this off of the 0.10 amount, it would essentially still be 0.10. Does that make sense?
Mm-hmm.
Yes.
Okay, so that's why we get to ignore the minus X for the common ion, because it's essentially the exact same number. The value of X is going to end up being so small it does not matter. All right, so everybody make sure you've got that so that we can turn the page and practice with the 3 practice problems on page 257.
Miss Baskin,
Yes, Sean.
you know how like in some of the problems it'll be like it'll give you like all the information and then you'll have to solve for one like what the molarity of one thing to then solve for like the molarity of a completely different thing. In some of these, does it ever do that with this? Like where it'll give you like, okay, you've did all this to find, you know, this solubility. Now find a different one.
No.
Okay.
Yeah, not on this. This is basically the last type of problem that could exist with KSP, with equilibrium, solubility equilibrium. So like the free response question we're going to do on Wednesday, you'll notice that this is one of the later types of sub questions that they would ask. So it would be part of a much larger question. And it's one of those things where, again, we're not trying to remember 100% of all chemistry that exists. We're trying to get a maximum number of points possible. So if this happens to be the kind of problem you don't remember, it's not going to be the worst thing in the world because there's all the other problems involved with this equilibrium stuff that you're going to be fine on. So, okay, so let's turn the page. Okay, so these are the practice problems on the next page. I'm just ignoring the stuff at the top because why not? Okay. Okay, so number 1 says calculate the molar solubility, all right, so that's M, of silver iodate in 0.12 molar sodium iodate. Now again, on the AP test, they're going to provide you both with the formulas and the KSPs. So the formula for silver iodate is AgIO3, and the value for the KSP there, since they would have to provide that for you, is 3.2 times 10 to the negative 8. Okay, so on the AP test, that's what they'll provide to you. They would provide that information there in blue. So sodium iodate, this is then the source of my common ion. So the formula for sodium iodate would be NaIO3. There's no subscripts there, so iodate, all right, my concentration of iodate is going to be what?
0.12.
Yeah. There's no subscript, so I don't multiply by anything. It's just the 0.12. So what we care about is silver iodate. So that's what we're going to write out an equation and an ice table for, right? Ag plus iodate, ICE. I get to ignore this, right? Because it's the solid. Don't care. What am I going to write for my initial line?
0.12.
0 on the silver, 0.12 on the iodate. What is going to be my change line?
Plus X on both.
Plus X on both, because I don't have any coefficients right here. So my equilibrium line would be
plus X and then 0.12 plus X.
Yep. So my KSP expression would just be Ag plus, iodate minus, and then plugging in the numbers, I've got 3.2 times 10 to the negative 8th. My Ag is X, and I am again making the assumption that my iodate is just going to be 0.12. So we're just going to say that that's what this is. And then if you plug that in, all you need to do to get X is do what?
Divide.
Divide.
Point 12.
Okay, so go ahead and divide and see what we get for 2 sig figs.
.7 times 10 to the negative 7.
Mm-hmm.
All right. I got negative 8, but I'm not sure if I did something wrong.
Yeah, I think you have an extra times 10 in there.
Okay.
Try it again. 3.2 EE negative 8 divided by 0.12.
Okay, yeah.
Okay. All right, so on the next problem, I can set you up with the same information they would give you. So molar solubility, again, they're looking for M. Lead to iodide, the formula there, PbI2, and the value for that KSP is 8.5 times 10 to the negative 9. The thing that is producing my common ion is this. All right, so my concentration of iodide is 0.10. So go ahead and set up your problem the same way we set up the first one. The thing I will note that is different about this problem is this guy right here is going to play a factor in your setup, both in the KSP expression itself and in your change line. So try and set it up and let's see what you get.
Miss Baskin, in the initial for I, since there are two of them, do we put 0.2 or do we leave it as 0.1?
You leave it as 0.1 because it's coming from the potassium iodide.
Okay.
Miss Baskin,
Yeah, he is.
when we after we write the KSP,
Mm-hmm.
and like we put in all the exponents, like we make the coefficient the exponent.
Yes.
So do we drop out the 2x still?
Yes.
So, but then do we square the 0.10?
Yeah, you have to. It's part of the expression.
Okay.
What are you getting for the value of x?
8.5 times 10 to the
Yep,
negative.
to negative 7. Yep. Does that make sense? You with me?
Yeah.
Okay, so looking at number 3, what is the one subtle difference in the third problem from the first two?
You gotta go from moles to grams per liter.
Yep. So the previous problems were just asking for molar solubility. This is grams per liter. So again, the last step, if this is molarity, the last step will be multiplying by the molar mass to get the final answer. So it's the same setup. So here we're looking for barium sulfate. Again, barium and sulfate, those charges cancel out. So there's no real subscripts here to deal with, which makes life easier. The KSP value for barium sulfate is 1.1 times 10 to the negative 10. The barium nitrate provides your common ion. So that means your concentration of barium here is going to be 0.050, which while that is smaller than the 0.1 and the 0.12, you can still see, like, based on this exponent value on the KSP, X is still going to be really, really small. We're still going to be able to make the assumption that we can just ignore the plus X here. So that's the information you need there. So go ahead and set up this one, and we'll see what you get for the value of the molar solubility X. And then remember that you'll have to multiply it by the molar mass to get the final answer of grams per liter.
Ms. Baskin, we're writing out the equation for the barium nitrate, correct?
No, the barium sulfate.
Oh.
Because remember, nitrates don't ever make solids.
Okay. Okay.
And Miss Baskin, when we never mind. I think I know the answer.
Can we like private message you to check? I'm just gonna wait actually.
All right. Are people agreeing with the answer that I got?
Yep.
Yeah.
Oh, I think I messed up.
That's what I got.
I messed up, and I see what I did.
Okay.
Okay, so
I can't.
so okay. So when we drop the portion of the equilibrium, we're
Mhm.
dropping the extra variable.
Yes.
Okay. I was working too fast. I dropped the actual value.
You
So I
dropped
just
the
had
0.05.
x squared. Yeah, so I just had x squared, and I was like, this is not what I got. This is not what happened.
Yeah, no, that would just solve the regular solubility, not the solubility in the common ion.
Mhm.
Cool. So that's it. That is literally the last page of section 4.4. So if you read my email or the weekly plan I sent out, I am asking for the 4.4 questions on Wednesday. And then for class Wednesday, we're going to work through free response question. So it's question number 1 from 2001, and I included a link to the PDF that you can go ahead and print if you have a printer and want it printed out. Otherwise, you can just work on notebook paper on Wednesday, but you can see that this is like the standard way that an solubility equilibrium problem will work through progression in the steps, again, where there's easy points at the beginning to progressively harder questions towards the end. And then today I'm going to make the quiz in AP Classroom, and we'll see how that goes. So I'll have more information about the format of the quiz on Wednesday.
Mhm.
Miss Baskin,
Yes, ma'am.
did you find out about the AP test and the
No,
stuff?
I haven't
Okay.
gotten any any feedback at
Uh-huh.
all about that. So, yeah. All right. So I've got open office hours from 4 to 5 today, and then AP specific office hours from 11 to 12 tomorrow. And then as always, you can send me pictures or questions about any of these things. And hopefully by Wednesday, I'll have all of the makeup work and the 4.3 questions and stuff you guys have submitted. I'll have all of that graded and entered for you.
Miss Baskin, did you ever end up figuring out the thing about the AP test? About
No,
us?
not yet. Kayla asked that same question when you got kicked out.
Yeah, like 3 times. My iPad.
I know. I keep letting you back in though.
It's crazy.
So, all right. Well, unless you guys have any questions, that is it for today. Short and sweet.
All right. All right. Bye.
Thank
Bye.